Thank you for joining us this afternoon for this next in the ATA educational webinar series, NX Fibersim and Simcenter 3D Laminate Composites, a complete integrated system for laminate composite design, analysis, and manufacturing. I am your host, Scott Tebow from ATA Engineering, and our speaker today is a special guest, Andrew Jabola from SDA Software. Before we launch into the technical presentation itself, I would like to introduce our sponsoring companies, ATA Engineering and SDA Software. So ATA Engineering is an employee-owned small business with a full-time staff of almost 200 with offices across the United States. We are an engineering services company that is also a Siemens value-added reseller for Siemens engineering software. And we operate under the philosophy of sell what you use. So the software that we sell is pretty much the software that we use. Today's webinar is on a piece of software called Fibersim, in addition to the Simcenter 3D Laminate Composites, that we don't use as much as others. So we, following our own philosophy, invited one of our fellow value-added reseller partners, SDA Software, who are experts at Fibersim and do use it quite regularly, to present today's material. ATA operates in a number of industries, principally aerospace and defense. But we also have a very substantial themed entertainment practice. If you think about roller coasters, animatronic figures, movable attractions, and that sort of thing. But we also work in industrial and mining equipment, consumer products, energy, and many other fields. We serve our customers nationwide from our offices spread across the United States, our principal headquarters, our principal office is in San Diego, California, but we also have offices in Los Angeles, in the Bay Area, Denver, Albuquerque, New Mexico, Huntsville, Alabama, where I am myself located, and in Herndon, Virginia, outside Washington, D.C. ATA provides services for design, analysis, and test, and we love to be faced with our customers' most challenging engineering problems. ATA Engineering is also a Siemens Platinum level solution partner. We provide licensing and support for a wide range of Siemens products, including NX, Nastran, VMAP, Star CCM+, Simcenter 1D, Simcenter 3D, Teamcenter, RuleStream, and many others. As an interesting note, ATA Engineering also is not only a preferred training provider from Siemens for the Nastran FEA solver, but we actually are the authors of the Nastran training material that Siemens uses worldwide, which we provide to Siemens under contract. We provide hotline support for all our customers from 8 a.m. to 8 p.m. U.S. Eastern Time. If you'd like to know more about the products that we provide from Siemens or access our wealth of resources, please visit us on our website at the link shown. You'll find that you'll have access to dozens of previous webinars just like this one, but on a wide variety of different topics. There'll be white papers, presentations, tips and tricks, tutorials, and many other resources, all provided for free. Our other sponsoring company for today's webinar is SDA Software. SDA Software, like ATA Engineering, is a value-added reseller for Siemens Digital Industries software. They have a team, as you can see here, and that team is made up of aerospace and mechanical engineers with a focus on engineering science and mechanics. They have multiple Fibersim experts on their staff and know perfectly well how Fibersim fits into the Siemens analysis ecosystem as well, which in the context of today's presentation is Simcenter 3D. Here are some recent SDA projects in space, aircraft, unmanned aerial vehicles, and other projects. And there is a big focus on, of course, composites design as part of these projects. SDA sells the NX Fibersim product, which is also available for other CAD tools such as CATIA or Creo, but today we're going to be looking at it in the context of NX. And there are a number of options for Fibersim that are available as well. They provide training for Fibersim and support for these products. Today's speaker is Andrew Jabola from SDA Software. Andrew has been providing structural analysis support for a wide variety of aerospace programs for many years and is an expert on the Fibersim product and on Simcenter 3D laminate composites. Take it away, Andrew.
All right, I want to say thank you very much, Scott. Again, my name is Andrew Jabola, and I'm with SDA Software. And today I'm going to be presenting Fibersim and Simcenter 3D Laminate Composites, a complete integrated system for laminate composite design, analysis, and manufacturing. But before we start, I want to discuss a couple challenges that projects that use composites might run into. One of the first challenges is really communicating between the analysis group or the engineer design to manufacturing. Many times engineers will use PowerPoint with images or other methods to try and communicate their ply layups, what the analysis ply layup should be to the manufacturing group. Now, this could lead to errors such as maybe not identifying a boundary correctly for manufacturing and you end up with an incorrect part. So what is a way we can streamline this process of getting our analysis intentions to the manufacturing group? Another item is actually once the manufacturing group has come up with the part, trying to verify the performance of the as manufactured part. Many times when you're doing composite parts, high curvature could lead to fiber orientations not matching exactly what was analyzed, or you might have overlaps or other aspects that aren't captured in the original analysis model. Many times these may not prove to be an issue, but you may want to verify that. So how can we show, prove out the performance of the part as well? We're going to show how Fibersim combined with Simcenter 3D is able to solve these issues. So our agenda today is we're going to first discuss the challenges, which we just mentioned. We're going to show the typical engineering process for a composite structure. Then we're going to dive a little bit more deeper into the composite integration with Simcenter 3D and also Simcenter 3D with Fibersim. Then we're going to go ahead and actually demonstrate this live with both Simcenter 3D and Fibersim in the NX products today. After that, we will conclude the demonstration and take questions and answers. So first of all, let's discuss a typical engineering process, again, specifically for composite parts. Obviously, at the beginning of a program, we have preliminary design or definition where we're figuring out what the layups need to be, how thick or how many plies we need. Maybe we need to drive stiffness into certain areas. As we continue to mature in the design, we start doing more structural analysis and verification. We start going from typically very much a zone-based type methodology and end up coming up with detailed plies. As we continue this iterative loop in this section of the part, we go from a very preliminary design to the final manufactured part. Obviously, during this process, we want to make sure that we verify performance of the manufactured part. Once the engineering teams are satisfied with the design and we have a product that can be made and still meets our requirements, we begin the production side and end up with our manufacturing data set and end up with vehicle production. Now, the Siemens suite of tools provides lots of options for being able to tackle all phases of engineering, whether it's exploring the design space to creating the geometry, all of this while being managed as well internally. So here we have a couple of products we show here, such as Simcenter HEEDs for doing optimization and design exploration. We use NX CAD a lot for geometry design and also for tooling and many other of the design and manufacturing aspects. SyncroFit for assembly analysis. And all of this data is being managed in Teamcenter. But today, our focus is primarily in the composites design definition to performance validation range. And we're going to be highlighting the integration between Fibersim and Simcenter 3D. So one thing we want to mention is the composite integration within the Simcenter package. One of the beauties of Simcenter is that it's able to take design data or composite design data from a multitude of sources, such as Fibersim, obviously, also CATIA CPD and Simulate, just to name a couple. And from this, we're able to take this data and generate analysis models for a variety of solvers as well, such as ANSYS, LS-DYNA, Abacus, and of course, our own solvers of Simcenter, Nastran, and SAMSEF. Now, one of the additional capabilities is obviously between Simcenter and Fibersim is the bidirectional capabilities between the products. We're able to take ply data from the analysis models, send it to Fibersim, and then we're able to take the manufactured data with the layups, angles, and everything else and send it back to Simcenter. So this bidirectional capability is a very powerful integration between the two products. So here we're just kind of showing the process of being able to use both products concurrently. Early on, we might start off with a preliminary design, and you may have zones that identify different locations that we might be able to work with. The analyst will then be able to thicken up these zones and determine, an initial layups. As the project progresses, we're starting to include more details, such as actual drop-offs and other layup zones. Eventually, you'll end up with a manufactured part, and you're able to, again, communicate this data back and forth between Fibersim and Simcenter. Just a little bit more detail, we can do this through the Simcenter and Fibersim's capability of exporting HDF5 files, allowing communication of plies between the two products. So we can develop the ply layups originally in Simcenter 3D itself with the different laminates. And then we're able to communicate that to Fibersim. This information gives the Fibersim engineer the exact boundaries of the parts. So there's no guesswork on knowing exactly where your plies are on the part or what the layup is. And then using the same techniques, we're able to then export that data back and integrate that in, providing this bidirectional link. So we're going to go ahead and actually show this process on an existing part that was used for that we'll discuss here shortly. So our objectives during this demonstration are really two phases. Our first phase is to kind of communicate the ply layup requirements from Simcenter 3D via the export plies to Fibersim function. So here we're starting off with the analysis model, communicating that data out to Fibersim. Then the Fibersim engineer is able to take this data and then create the designed layup. This brings us to the next phase, which is verifying the manufactured part. So here, we're going to take the detailed manufacturing data, bring it into Simcenter 3D, and then verify our performance of the manufactured part versus the analyzed part. But before we do that, let's give a little bit of background on what this part exactly is. This part is a composite piece that was quite a bit of a challenge for the manufacturing side. The high curvature required us to do a lot of splicing, and this part was we were able to prove Fibersim's capabilities with this part. This part is a prototype filter wheel, also known as an element wheel, that was built during the pre-phase A studies for the Wide Field Infrared Survey Telescope, or now known as the Nancy Grace Roman Space Telescope program. This is a manufacturing demonstrator where we took a design, we analyzed it to meet requirements. The high amounts of curvature was actually needed to try and avoid a bunch of different light paths. And the composite nature was to try and reduce the CTE issues of deformation of this part. What we did with this part is we actually were able to produce the ply layups in Fibersim, therefore digitally creating our plies instead of spending many hours and wasted material trying to generate this data or actually generate these layups by hand. So we took what would have taken about 4 to 5 weeks of hand layup and reduced it to a single week of cutting out the plies. Fibersim was able to generate the flat patterns from the, and then we cut these out. And then we were also able to very quickly generate the laser tracking data for this and be able to actually produce this part very quickly, eliminating waste and increasing our efficiency in generating this part. On the right here is shown the complete parts. So we have 6 filters, and there's also 2 other optical locations as well that were used for different hardware. And so even though we didn't go past testing or really past manufacture for this part, this definitely proved some excellent capabilities with Fibersim. And today we're going to actually continue this process and actually show some of the analysis integration with Fibersim as well using this part. So now we're going to actually dive into here and show our process of going from the analysis model all the way to detailed ply development. So here we have is the actual analysis model that was used during the WFIRST program from a while back. Now this particular piece was actually used for the random vibration testing that was going to occur early on, but it's also proved very useful for demonstrating these processes with Fibersim. Now this part was already has the analytical layup developed. As an analyst, we have defined a couple different ply layups here. So for instance, we have here a 24 ply zone of different layups here. Here we have a 20 ply zone. And here we have a 16 ply zone. Now, typically, as analysts, if we were going to communicate this via the old methods, we would probably create a picture of different plots. Here we're going to just show the laminate zones and then have little arrows on a PowerPoint pointing this is 16 plies of quasi-ISO, this is 20 plies of quasi-ISO, and this is 24 plies of quasi-ISO. But instead, we're going to actually ensure a better communication path by exporting this data and sending it directly to Fibersim. So at this point, the analyst simply has to right-click on his layup and export plies to Fibersim. In the interest of time, I've already created this part, but here I would simply edit this file and send this over to Fibersim, and we'd be able to create this export. At this point, the analyst has communicated the data, and we'd send this file over to the Fibersim engineer. So on the other side, while the analyst is working on getting this data, the Fibersim is likely creating the mold surfaces and prepping the model for the development. So here we have the actual final piece shown here from a CAD model standpoint. And here he would likely generate a mold that we're going to be laying up on. So this is actually the mold that was used for the manufacturing process. And then from this, we're going to actually choose an analytical surface for Fibersim. So at this point, I'm going to go to a clean part here and open Fibersim. Again, all of this is integrated within your CAD package, in this case NX, so that data remains attached directly to the model. Now, as the engineer, we've already defined a laminate that we're going to be laying up on and a couple rosettes that we're going to work with here. So now the Fibersim designer is going to go ahead and import this data from Simcenter that we had just created earlier. So we'll go to Analysis Ply, CAE Exchange Format, select our file. We're going to do SC3D to Fibersim Export. And here we can actually view the analysis data and bring in our ply information. So what we have brought here is 24 plies, which is the top plies at the center here. We've created a couple temporary materials and rosettes. What we'll do is we'll go ahead and link this to information. There might be, or material information. There might be times that the analysis material data won't be the same as the Fibersim data. So we can then link this to our Fibersim data, which might have different parameters. We might be able to link we would link our rosettes. So perhaps in this case, we're just going to go ahead and link the first rosette and bring that in. And then here we actually have our plies themselves. Again, we have 24 plies. You can see that they have their layer IDs and orientations in the part here. And if we click through, you can see that our FIM data is actually being overlaid on the part. Now, there's lots of cleanup options in the part here. So we have the ability to refine curves, set as full body, import data, things like that. So we might go ahead, let's go ahead and project the curves. This ensures that we have them onto the actual laminate surface. And then we'll go ahead and import the data into the model. So this is actually bringing in a ply, analysis name ply 1024, layer 240, or step 240 with an orientation of 0 into the model. And so we can start doing this for a variety of the different plies in the model here. So here, again, I'll do the same steps, project curves, import data. And kind of repeat this step for one or two more plies. So project curves and import data once again. So from this, we're again bringing in the boundary information that was defined by the analyst, eliminating the guesswork that you might have from other forms of communication. Now from this, we have the different layers. Now again, we only imported 3, but you'll see that we have the ply name as related to the analysis model, the step as defined in the analysis model as well, and the orientations, giving us a very clear answer or clear definition of the engineering intent for the part. Now the Fibersim analyst can go ahead and generate the ply, and then he'd proceed to go about actually starting to work on splicing and creating the manufactured part. Now in this particular case, you can see due to the high curvature of this part, we're going to have to spend some time really splitting up this geometry. And in the interest of time, we're not going to actually show the process of working with the Fibersim manufacturing side. We do have other demonstrations and videos of that on our website, and or reach out to us if you have questions on that. But now what we will do is then take this information and go ahead and work with it to create the final part. So the Fibersim designer is going to take this, split it up, and end up using this information to generate a final piece. So here we've shown the first steps of this, of going from the analysis model, communicating the data via the HDF5 format from Simcenter, and then importing that into Fibersim. And then we start the process of doing the detailed ply development. So this brings us to the next step. The Fibersim designer is going to go ahead, come up with the detailed ply layups, work on building the overall information. And then once he is done with that, he's able to produce an export out to Simcenter. And then we're able to use that information to update the finite element model. From this, we can then verify performance of the part to ensure that we are still meeting our requirements. So to demonstrate this, we're actually going to go ahead and return right back to the part we were in. Now in this case, moving to the next part, we are actually already at the point where we have the production layup in this part. So coming back into Fibersim, here we have the different plies. So as you can see here, here's our first set of plies, our second set, third, fourth, fifth, and so on and so forth. Now, some of these parts ended up having to be darted quite a bit to ensure that we could actually manufacture this. Here, we're going to go ahead and do producibility on one of these parts here. Now, one thing to note is we had specified during this design process, the designer wanted a radial rosette. So the idea is that we want the zero direction to kind of propagate outward from here. But if we look at the ply itself, I can't remember which one I did. There we go. Ply 2, for instance, here, A-4, we notice that perhaps even though this is supposed to be let's review this, a 45 ply here. And if a radial rosette was coming across here, we might see that we might be deviating a little bit from this. This is probably closer to 40 or even 35 degrees. So sometimes, just again, due to the complex curvature of this part, we had to kind of accept that some of the plies may be a little bit off from each other in that respect. We can verify this even more with our design station functionality. So here, what this tool does is this actually will punch a hole through all the plies and give you a detailed analysis through a core sample to actually show you what layups exist there. So for instance, maybe we're interested in the layup, let's do right about here. So here, we'll go ahead and do a core sample. And what we'd expect is a relatively low error in the angles between each other. So here we have 24 plies as defined by the analyst. Again, we have about a proper percentage of 45s and 90s. But the one thing we notice here, as well, is that for the most part, these are relatively close to either 0, again, this is minus 180, and 45. So we're getting a relatively consistent ply layup. But this isn't so true in perhaps regions such as here. So again, we're going to go ahead and perform another core sample. And what this will do is, again, we're punching through and we're going to get the layup in that region. Now here we can see we have 16 plies. And what we're going to do is we're going to start off from our base ply with a 0 and measure the rest off that. So you can see here again, we have a relatively consistent number. But if we start looking at our plies, we can see 0, 58 degree, 25, and minus 15. So there is some deviation here from what we would have gotten from the as manufactured part as compared to the analysis part. Now the question is how much does this actually impact the overall behavior of the part here? So we're going to be able to answer that and show that directly using these tools here. So at this point, the analyst is going to go, or sorry, the Fibersim designer is going to go ahead and he's going to make one quick adjustment. One thing we may need to do is we may need to adjust the resolution of the part. One of the nice things within Fibersim is that we can specify a cell size, and usually you want this to be pretty close to the part here. And so here we're just doing net producibility. If this resolution doesn't match the FEM, that could be an issue. You may not get a good export. After that, we're going to go ahead and export this data out back to Simcenter 3D. So from here, we'll go to Export, Analysis Ply, CAE Exchange Format. Now here we've already defined one of these groups, so we're just going to go ahead and edit this. So here we've defined what components we're going to use. So in this case, we have 280 flags or 280 plies that we're going to be exporting out of the part file. We're going to use the net boundary. Here are a couple other options we can play with if we need to. In this case, I just said use manufactured part. And here we specify the part and where we're going to go ahead and export. At this point, we could go ahead and click the export button. But in the interest of time, we've already exported this part. And what we see here is a report from the last time we exported this just 2 days ago. So we exported 280 plies. Here's a couple warning messages. You know, maybe if we were really concerned about verifying the part manufacturability, I might want to check ply 14-A-1 and 7-A-1 as well. But overall, this is a very clean export. So at this point, once we have exported the part, the Fibersim designer is ready to send this information back to the analyst. So the analyst is now going to take that HTF5 file and work with it into this part. So here, we're back to the analysis model, and we're now ready to update this part. One thing I want to illustrate here just to show is that when this part was originally analyzed, we specified just simply a very similar orientation to the radial rosette that we had earlier. We were simply just radiating out from the center here. So we show that on the rosettes or the material direction, and that's how it was defined. Again, it wasn't as much of a concern for this particular part just because we were trying to keep it a quasi-isotropic part file. But now we can actually increase the accuracy of our laminate development. So here, we're going to go to Laminates, Import Fibersim Layout. Here we're going to specify the mesh that we'd like to interpolate the data on. So I would be grabbing this mesh right here. And then, we can specify a search distance. You might change this depending on the accuracy of your if there's any idealization on your mesh. We can change some of the other options as well. And then here, as you can see, we've already selected the file. But we go ahead and select the Fibersim to Simcenter 3D export file that we generated earlier. In this case, we're not going to import materials because we are wanting to use our analysis material data instead of the Fibersim data. And we'd go ahead and import this into our model. So at this point, I would click OK. But again, in the interest of time, we've actually already done this import and have a Fibersim layup here. So as soon as we have an import into the model, we're going to get something that looks like this. I'm going to go, we do have polygon and geometry shown. Here, we can actually see our different ply flags illustrated in the part. So if we start scrolling through, you'll see the names of the different flags that we have imported. And you can see these locations actually interpolated on the part as well. So we're just scrolling through here. One thing we may want to do as an analyst is we'll probably want to go ahead and make sure that the material is actually using our analysis data. So this PPG 3K value was pulled from our Fibersim database, but now we can go ahead and change this back to our analytical database. We'll go ahead and hit OK. Actually, before I do that, I'll go ahead and show that we have our thicknesses from our Fibersim data, as well as, again, our different plies. And again, we have 280 flags, just to make sure that we're matching what we have in Fibersim. At this point, we're ready to actually create all the zones of the property. Now, when we hit compute zones, what this is actually doing in the background is creating all the PComp properties that would be identified for the plate model here. And all these different areas have the different thicknesses of the parts, the different angles, and any fiber deviations for the layup. In cases of where we have ply overlaps, which is typical for a lot of other aerospace products, you would actually see those overlaps placed in the FIM. So you would actually be capturing the actual drop-offs instead of the analytical ply drops that are usually not modeled on more preliminary design FIMs. So once we have computed these zones, what you're going to actually see is quite a number of PComp zones generated in this part. I think what we'll see is somewhere around, 9,500 zones that were generated in this process, or 9,200. So each one of these are actually different PComp cards inside this part. So just to help view this a little bit better, we will go ahead and change the color display back to collector. And now what we can do is we can actually verify how this interpolation occurred. Now, the first thing I typically do upon an import is I will plot the thickness contour of the part. what this is showing is the actual thicknesses of the plies. And what we see is we have a very good import of a fairly clean 24 ply, 20 ply, and 16 ply zones. Now, again, if you do this with other aerospace parts where you typically have overlaps, you're actually going to see those overlaps and ply drop-offs from the manufacturer data in the part. One very good verification that your Fibersim export came through properly. The other thing we can do is we can actually take a look at the actual layups and fiber orientations. So here, let's go ahead and find a little bit more interesting of a ply. Let's do this guy right here. So I can actually right click and view fiber orientations on the part. So again, this is the data from the Fibersim model for this particular ply. So again, using a radial rosette, this is probably a 45-degree ply. We can see how here we're matching relatively close to the 45-degree angle. But when we come up here, this is probably closer to 40 or even 30 degrees just because of the layup of how this part was laid up across this piece. So now we're actually capturing that data in the model as opposed to not capturing it and assuming that the analysis model is the correct way only. Another thing we can do is actually verify this and kind of view the laminate in certain regions. So, I might click here. Let's do ply sketcher. Again, we have 16 plies, but you can see here our angles, if we were to subtract 5 from here, aren't exactly 0, 45, 45, 0. So as we click through the part, you can see how these angles change throughout and how we might see some of these fiber deviations in the overall structure. So again, the reason we're doing this is to capture data such as ply drapability and any overlaps in the part, and then we can actually use this to verify our performance as opposed to taking a guess analytically. So at this point, as an analyst, we're ready to actually perform the final steps of performance verification of this part. So for this particular model, there's 2 metrics that we're interested in. First of all, we are interested in the modes of the part. We want to see if there's any stiffness changes between the parts. So we ran a solution 103 eigenvalue analysis here. The other thing we are interested in is thermal distortion. Do the parts behave similarly? Or if they don't, how far off from each other are they? So here we've actually done a thermal analysis from room temperature down to 170 Kelvin to essentially shrink this part during the analysis process. And what we're going to do is we're going to take a look at the translation of this particular optical element and see what the differences are. So in the interest of time, I've already run these analyses. So what we're going to do here is actually show side by side the information in the model. So here we're going to go ahead and set up a second view and bring in the 2 modes of the parts. And at this point, we will go ahead and synchronize these 2 views here of the model. Now, what we see here is that our first mode is very close to similar. We're only about 0.3 hertz off. As we start cycling through the modes, you can see 81.28 versus 81.07. Here, some of the stiffnesses do change this by a hertz. But overall, as an analyst, I'd be pretty happy with the fact that we really haven't changed the overall stiffness of this part. We are trying to accomplish this as a goal. Now, of more interest, primarily to the optical group, usually during a stop analysis, for instance, structural thermal optical performance, we'd be interested in the relative displacements of these parts. So again, what we're going to show here on the left is the analytical model. So this is the as analyzed part. And on the right, we're going to show the Fibersim result. And usually when it comes to optical analyses, the deformations are very small. So even though it may only be 0.1 thousandths of an of a displacement difference between the two parts, that could still be critical. So what we're going to do is we're actually going to show the results here and just identify one of these nodes. So on this part, actually, let's go ahead and click this guy first. Grab this node here, place this into a window that we will be able to compare. Click this node and do the same step as well. And put that into our information window. So what we're looking at is the difference in deformations between node 6 million and 5. And overall, what we're seeing is that the deformations are very close to each other, but they're still slightly different. We can see here that we are 8.45 or 8.46 thousandths off on the Fibersim part, but 8.54 on the analytical part. Now, again, most likely this would probably still show a positive performance. At this point, as an analyst, we'd be sending this data to our thermal engineer or to our optical group to verify these deformations are still good for that optical element. But sometimes these small numbers can make a difference. And, perhaps at this point, if we do find issues, we could spend some time tuning that between the Fibersim layup and our analysis model and going through the iterative process of communicating back and forth to ensure that we still achieve our performance requirements. So what we have seen here, though, is throughout this whole process is the following. So we've shown now during this demo how we've gone from taking our analysis model, exporting this data via the Simcenter 3D export applies to Fibersim. From this, the Fibersim engineer is able to take this data and develop a detailed manufacturing model. And then from this, we're able to take that information back and communicate that and verify our overall layup performance. So in conclusion, we see that Simcenter 3D combined with Fibersim provides an integrated tool for composite design and manufacture. We're able to provide direct integration and communication between the analyst to the Fibersim engineer. By using this tool, we're able to eliminate errors by taking the guesswork out of your boundary development or your locations of your different plies. And so instead of doing the original methods of PowerPoint or who knows worse of email or chicken scratch, we're able to actually communicate this directly through the HDF5 export. Then instead of taking instead of guessing that, hoping that your manufactured part still achieves the performance values that you're looking for, we're able to confirm this by exporting the as manufactured data from Fibersim back to Simcenter 3D and then perform a final analysis for verification. So at this point, just want to thank you very much for taking the time to watch this webinar. And I will hand it back to you, Scott, to start entertaining questions.
Very good. Thank you so much, Andrew. That was a terrific presentation. We do have a long list of questions, and I'm going to get started with them. But I would ask our participants if you have any more questions that come up. In the interest of time, it would probably be faster if you just type them into the chat or the Q&A screen, and I will, tack them on until we either run out of questions or run out of time. The first question we have, Andrew, is Fibersim limited only to Simcenter 3D export?
It is not. So we are able to export that data to other tools such as FEMAP or even PATRAN. There are other options such as a BDF export as well, and several other methods as well. So we're able to actually export through a variety of methods, not just to Simcenter 3D.
Terrific. The next question is, what if we don't use NX for CAD? If we use Creo or CATIA, how would that work?
So that's one of the beauties with the Fibersim tool. Fibersim actually does work also on Creo and CATIA directly. And then if you aren't using that, for instance, if we're using SolidWorks, where our team's actually presenting a webinar on that very topic, you can still use the other tool sets and be able to work with Fibersim in that respect and be able to use some of the wave linking capabilities built into NX to be able to still handle that outside data and even outside design changes. As a side note, we actually have a program for one of our customers that we're supporting in SolidWorks, but we still need to do the Fibersim development. And so we actually use this exact technique to ensure that we're still able to make producible parts, even though we are not in the NX CAD product.
So a follow-on question is, so you're saying that I could use a different CAD system like Creo or CATIA or SolidWorks, but still use Simcenter 3D for the analytical portion if I wanted to.
That is correct. One of the beauties on the analysis side, I guess I was mentioning the Fibersim side earlier, is that Simcenter 3D is a pre and post neutral to both solvers and different CAD systems. So again, one of the capabilities of being able to deal with the geometry idealization, for instance, that's a challenge. You can use the wave linking within essentially the Simcenter 3D product to be able to bring in design changes from your other systems and integrate that into your analysis model, and then save yourself some of the time that may have been spent on having to manually regenerate your new FIM for every single design change.
Terrific. This looks like a question for me. Are Fibersim and Simcenter 3D laminate composites supported by tokens? And the answer is yes, but with a limitation. So Fibersim is supported by NX tokens, and Simcenter 3D laminate composites is supported by Simcenter 3D tokens. If you're using another CAD package, not NX, then you wouldn't be able to access Fibersim through tokens. You would need to buy Fibersim for Creo or Fibersim for CATIA. But if you have a token pool that includes both Simcenter 3D tokens and NX tokens, then you would be able to run Fibersim using tokens for both sides of it. Next question, does analysis geometry have to perfectly match the layup surface data for the bidirectional transfer to work?
It does not, although your accuracy will be a lot better, especially for the as manufactured part. There have been times that I may have removed a fillet or something of that sort. And then what you do is you increase the search distance from your manufactured layup. Now, again, this could be an issue of some of the accuracy. I've seen cases where it doesn't always match up. So it's usually better to set up your mesh to be able to match perfectly, especially if you're usually using it during the final phase of that analysis process for that manufactured part verification. But this case here with this FIM actually, this FIM actually had been slightly different for a previous run, and I had done a very similar method of interpolating that data onto the old mesh. So using the search distance, you're able to still work with that even if it's not exactly a perfect match.
Gotcha. Next question. Are there different levels of Fibersim and how do they differ?
That is actually an excellent question. What we can do is we can actually table that question. That'll be a good question for our team. I do know that there are various different bundles that you can buy. And then also through the token system, obviously, that is another option to be able to ensure that you do have access to everything. But again, that might be a good question for us to table, and we'll be able to coordinate with you on that offline.
Okay. And the last question, and by the way, I do invite anybody who has a final question to put it into the chat. I don't have any more besides this last one right now, but if you have any questions, please type them in and we will be happy to take them. Oh, I do have an answer from one of your colleagues, Andrew, that says that Fibersim is a core product, but does have multiple add-ons that you can custom configure for different specific needs. So if you either have access to Fibersim already through tokens or are interested in licensing it, then by all means, reach out to me or Andrew, and we'll be happy to help you. The last question is, how else, meaning apparently besides this bidirectional transfer with analysis, et cetera, but how else does Fibersim assist with the manufacturing process?
So one of the things we didn't really highlight in this particular video, or particular presentation, was actually a lot of the manufacturing capabilities of Fibersim. We do have other webinars that really discuss this in detail, showing that. Actually, if you go back a while back, you'll even see one for this particular part that I did, I think it was 8 years ago. But from Fibersim, in addition to verifying the ply drapability, ensuring that we're able to actually produce this ply and lay it up, we can generate the flat patterns. Again, as mentioned earlier, for this manufacturing tech demo for NASA, we were really able to reduce the time for manufacture by checking the producibility, actually getting plies that were able to lay up on the part. And that was a difficult with this high curvature part. And then we're able to verify that, produce the flat patterns. From that flat pattern data, we can send that out to a ply cutter. I would love to say that we use that at NASA, but we were a little bit more simple, and we're able to just use the patterns and cut them out by hand for this particular piece. But also we're able to produce other data, such as the laser tracker data, for instance. In the previous couple images ago, you may have seen a green line around one of the plies. That data was actually produced. I was able to get that out of Fibersim and have it on the laser tracker projecting data within 20 minutes of that information. Also, we're able to produce, for other cases, the manufacturing ply book data. So being able to produce the communication documents after you finally come up with a verified part. And so being able to produce the ply books, produce any other data as well. There's a lot of other capabilities that we have demonstrated in other webinars. And again, if you have any specific needs, definitely feel free to reach out to us to ask those questions on the manufacturing side.
Very good. Well, I'd like to thank our speaker once again. Thank you very much, Andrew. We certainly appreciate your time and the wonderful presentation that we saw today. And I would like to remind everyone that if you would like to reach us about anything you've heard today, you've seen Andrew's contact information earlier. Here is mine. We'd be happy to hear from you and provide any further information that you might require on Fibersim, NX, Simcenter 3D, or any of the other products we sell and support. Thank you for joining us today for this and the next ATA educational webinar series on Fibersim and Simcenter 3D laminate composites. Thank you for joining us, and please watch your email for the next in the ATA educational webinar series, which we do regularly. Thank you very much again for joining us.